Hello, class. I am going to try to do a lecture on the Smith chart and all of the great things that the Smith chart still gives us. Originally, the Smith chart was really an analytical tool like a slide rule or something like that, that basically turned a mathematical equation into graphical equation. But still today, the Smith chart can, show you so much about matching. It's usually used for matching antennas or antennas with waveguides attached to them to the source of the signal, right? But anyway, I was thinking, how should I do it? Should I actually put all of, things on a Smith chart and sort of show you everything and then try and get it and turn it sideways and see if you can see it and then do it in HD or hold it up here and change the focus? And, what I realized was, and I'm going to do that with the next one, is I'm just going to sort of go through the Smith chart and draw the Smith chart myself. I'm going to try to do this. Now, I do this in class when I teach this course, so I'm not sure how it's going to go here as far as drawing a big circle. And what I really needed was a protractor, but I don't have one. So I'm just going to have to, God, could I just lay that underneath there and trace that? No, no way that's going to happen. So what I'm going to do is to just make a big circle. Well, that's not so bad. I mean, that's not a circle. It's much more of an obloid, but it's still, sort of, it's not so bad. Anyway, I'm keeping it like that. So what we've got here, let's say that we've got a line right through the center of this. And now, first of all, to start our discussion about the Smith chart. And here's the complete Smith chart. Blackmagic is the one that's designed, sent it out, but it's the same. You can get them at a whole different places. It just happened to be, I downloaded it off that website. I'm not even sure if it was called Blackmagic. But the line through the center of it. Now, what is the Smith chart? Here's what the Smith chart is. When we think of, and impedance, we know that impedance is Z equals R plus JX, right? And so inside our reality, we don't really know a lot of negative resistances. Now, we know negative impedances. Negative impedances would be capacitive, and positive impedances would be inductive, right? But we don't really have positive and negative resistance. So what Smith did is Smith said, hey, what I'm going to do is I'm going to take that complex plane of resistance, my impedance plane of resistance and reactance, and it goes from minus infinity to plus infinity, right? That's what the Cartesian coordinate system does. If this was my reactance and this was my resistance, then we would say that this guy right here, that point in space, would be my impedance, because my impedance has a component that is resistive and my impedance has a component that is reactive. And it so happens I seem to have drawn it with a 45-degree angle, but of course that has nothing to do with it. The angle has nothing to do with it. It's just the two components, the resistance and reactive components of that. I thought that I would also at this point just bring up some other things. Now we know that Z is impedance. I want you to take this with you going forward because you're going to hear about it a lot more than you think you are. And then R is resistance. We're going to use it, of course, in the next lecture here with the Smith chart. But when we look at that, what is 1 over impedance? And I think everybody, has probably heard that that is admittance, right? 1 over impedance is admittance, and then 1 over resistance is going to be conductance. And then 1 over reactance is going to be, who knows? Does anybody know? Yeah, well, I would hope so, is going to be susceptance. Just so that you know the language of electrical engineering. And of course, what we're going to do in the next lecture is we're going to do some impedance matching using the Smith chart. And I'm going to do that using admittance rather than using impedance. And actually, we'll see how we can use the Smith chart to find out the admittance of a thing. But anyway, let's get to the basis of the Smith chart first. So what Smith did is he took this, because let's face it, R is always positive, isn't it? So if R is always positive, then we only really need this part of the complex plane, right? We need this first quadrant here. We don't need the second quadrant because that's got negative resistance. We'll never see that. We don't need the third quadrant because that's got negative resistance. We'll never see that. But we do need the fourth quadrant. In fact, the fourth quadrant is our capacitive loading, isn't it? And that would be positive R, negative X. And when we look up here, we know this is our inductive loading, isn't it? Because that's positive R, positive L. So or positive, I should say reactance. Positive reactance, that's right. Positive reactance up here, that's inductive loading. Negative reactance down here, that's capacitive loading. So what he did was he just bent these around into a circle. They're still going to infinity, but instead of them going to infinity in a linear fashion, they're going to infinity in an exponential fashion. All right? So if you think about it, we would start over here with 0, wouldn't we? Right? I would start over there with 0. And since we use the Smith chart as a normalized impedance, right? We would have 1 right in the center. And again, what am I doing here? What is this line right here? This is my resistance line, isn't it? So all along here is purely real, just like it would be if we were doing this on a Cartesian coordinate system. All along here is real. It starts at 0, and it goes to eventually to infinity, doesn't it? And we would see that here too, because this is 0, this is 1. If I wanted to find out where 1/2 is, then I would be right about here. That would be my 0.5. And then I could go down here to about 5. I'm just doing this generally. And then here would be about 10. And then here would be about 50. All right. I'm just showing you that this is an exponential scale that I have on my axis, but this is still my R axis, my resistive axis that I've got here. And what's this? This is my positive X, isn't it? So all along here, all the way up here is going to be my positive X axis. And all the way down, when I say X, I don't mean my X-axis like this. I mean my reactance axis, R plus JX. Let's not forget what we're talking about. We're talking about impedance here. So all of this is my reactance. This is my negative. So we would say that everything down here on the bottom is capacitive, right? So everything down here is, I'm just going to write it capacitive, right? R minus JX. And everything up here is inductive. Just like it would be on the complex plane, R plus JX, right? So this is my inductive axis, and that's my capacitive axis going to infinity. And so you could think, well, do these things go all the way around to infinity? Yes, they do. All right, so now let me draw, like we have on the Smith chart, a series of circles that are circles of positive R. Right, so everything on these circles is the same value of R. So that would be our 50. That would be our 10. This would be our 5 circle. Notice how all the 5 circles are, all the circles aren't concentric. They are all connected at the base of, I am not drawing very good circles, am I? Anyway, those are supposed to be circles. And then if I wanted something like, 0.5, 0.5 would probably be around about there, I'm just going to say. So I'm just going to try and draw a semicircle that maybe I can draw a semicircle better than I can draw a circle. Oh, that's pretty good. So you can see that all of these are circles of constant R. This is R equals 0.5. I've got, wait. Did I say that was? That actually is closer to, I would say, 2.5. You see, because, God, what am I doing? Yeah, of course it's going on 0.5, 1. Did I said 0.5? No, that's about 2.5. There's 5, 10, 50. Anyway, so these are larger. Thank God I write R. So this would be my R equals 2.5 constant circle for R. This would be R equals 0.5. I could put another one in there of about 0.2 would be about here. So that's my last circle that I'm going to stick in there before we start drawing the other lines. And of course, what are the other lines? The other lines are going to be the reactance line. So these are my resistance circles on the Smith chart, right? And you can see that for this, and of course this should go to infinity, and this does go to infinity. Look at it, 2.2, 0.5, 1, 2.5, 5, 10, 50, 5,000. It'll eventually get all the way to infinity. So we have the end of the road here is infinity. Now, is the same thing true for my lines of inductive or capacitive reactance? And the answer is yes, because perpendicular to each one of those circles that we have there, we have lines of constant positive and negative reactance. Now still, just like we've got up here, everything above this is going to be positive, everything below this is going to be negative. So how do we draw them? Well, they are coming out of here. And the one thing that we know is that they're perpendicular to each and every one of these circles. And I've drawn the circles horribly, but you get the general idea. So let's just see if I made these perpendicular to all of those surfaces going all the way back, I would have a series of lines that would look like this. Do you see how I'm making them all perpendicular to the, and of course that's how it would be on the complex plane too, isn't it? Isn't the resistance line perpendicular to the reactance line? Of course it is, and it is here too. And so that's what I've got here, a series of these segments that are coming out. I could draw maybe one more here, but I think you get the idea that these keep going in and out like that. And this would be on the capacitive side, so all of these would be negative, right? This would be like negative 50. And then down here, this is like negative 1.2. If I actually had the one coming straight up from here, let's just draw that. If I had that coming straight up from here, this would be 1.0. And as I keep expanding out, this would be about 0.7. I keep going out further and further so that this would be about 0.2. This might be about 0.4, something like that. And of course, these keep swinging around here so that this would be like minus 2. And this would be maybe minus 3, so on and so forth. Right? All of these, of course, are minuses because we're all south of the line, just like we are here. They're all negative down here, so everything down here is going to be negative, right? For the reactants. Now I've got the same thing that's going on up here at the top. Let's draw that one first. Well, that wasn't very good, was it? No, that wasn't. But I'm just going to draw some more down here. And now these lines, just like they were down on the capacitive side, are lines of constant positive. So this would be about 0.2, about 0.4, all positive now up here. This would be about 0.7. This would be 1. I'll just put a 1 up there. And then this would be something like 1.4. This would probably be like 3. And then we'd have other ones down here. And this would be like plus 50 or something like that. But of course, that is also going to go to infinity. And this one here, coming up from the bottom, is going to infinity too, isn't it? So all three of the axes meet at infinity over here on this side. And they all start at 0, just like you would expect them to. This starts at 0. So 0, 0, 0 is our coordinates that we've got right there. And so that's all that Smith did, was he wrapped all of those around. But what does it do for us? What does this do for us? It tells us a couple things. First of all, remember in the beginning, I said that we're always working with a normalized impedance, right? Z of D, small z of Z. And what small z of D is capital Z of D divided by Z sub 0. So with the Smith chart, what we're looking at when we're looking at the load, we're going to be looking at the small z sub L, which is the large Z sub L divided by the characteristic impedance of the line, right? So there's my load and there's my line, and that's how I would plot the load on here. And so let's just see what load would look like if I was going to plot it on this Smith chart. Well, first of all, this point right here, right in the center, is a very special point, right? because right at that point, I've got 1 plus J 0, right? Isn't this point right here? Just look at that point. Let's call that point A. And at point A, I've got 1 plus J 0. So let's say that I had a characteristic impedance of 50 ohms. Right in the middle, it would be purely real. Purely real. So if I figured out that I had an impedance of 50 ohms and my load impedance was also 50 ohms, right? Then there you go. 1 plus J 0. But that doesn't happen. And in fact, we would never need the Smith chart if all of the things were perfectly matched, would we? No, we wouldn't. But let's say that we've got some other type of thing, and I'm going to just pick one just to sort of show you some things about the Smith chart and how we can tell a lot of information about the mismatch of impedance in the Smith chart and what the load, what the voltage standing wave ratio is, and what the power losses are that we're going to have due to the reflection and in the line to the antenna match. So that's what I want to do now. Is I want to look at a point in space. And I thought that I would look at one that had a 25 plus J 25. So I'm just going to, this is an easy one. 25 plus J 25 load impedance, right? So 25 plus J 25 load impedance. Well, what will that give us? If we were looking at Z sub L, small z sub L for that, that would be 25 divided by 50, which is 1/2. So that would be 0.5 plus J 25 divided by 50, which would be 0.5, right? So what I want to do is I want to find my 0.5 on here. Well, there's 0.5 right there. And then where would 0.5 be along here? 0.5 is right about here. I'm going to draw that 0.5 because, oh, actually, I should have made that negative, shouldn't I? Yes, I should have, because I've drawn that as negative. I cannot find, here's what I'm going to do. It's a negative. And so is this one. I know, it's getting late. I've done 3 lectures today, and all of them take a lot of preparation. So that's 0.5 minus J 0.5. And here we go. There's 0.5. And here is minus J 0.5. So we follow that down, and we get a point right there. Let's circle that point. That point that I'm going to circle in blue is going to be called point B. So, well, that's A. So point B is going to be 0.5 minus J 0.5, right? Okay. Now, what we want to do to match the whole thing up is we eventually want to get this, and we want to put stuff together to eventually get back to that. Let's not get to that yet, because we've just basically, in learning about the Smith chart, learned a couple things. How would I plot? So I'm going to say that my load, right? That's my load. So this B at point B, this is going to be Z sub L, right? That's my load. This is where I'd like to get to for a perfectly matched load. Well, I can't. Well, I mean, I can't. It's not there. We've got to do something to get there. And this is not the lecture where I'm going to go into. In fact, this is the lecture where I forgot to time it and everything else. But this isn't the lecture that I want to go into stub matching. That's going to be the next lecture. What I want to do now is I want to look at what it is that we've got here. So if I were to draw a line, a straight line, I knew that calculator would come in handy for something. From where I am to where I want to go. Now, I drew that a little bit too far, and I did that on purpose because I want to bring this line out to show you on the Smith chart what I would really be doing with this. Now, first of all, this right here, this line, I'm going to say right here, that length on the Smith chart is proportional to the reflection coefficient. So if it's proportional to the reflection coefficient, then it's also proportional to the reflection coefficient for power, which I'm going to talk about. It's also proportional to the VSWR, because isn't VSWR and the reflection coefficient related by an equation? That's right. So the distance on here tells us everything. This is called the VSWR, the constant VSWR radius, right between there. Now, if you look at these large circles that we've had coming out from the side, these are circles of constant R, constant R. Now, everywhere else around them, it's got also, you know, like down here, this might be R minus J2, right? But it still starts with R, 2.5 minus J2. If it was up here, it would be 2.5 minus J.5, right? So all of these circles are constant resistance circles. But when we look at this length right here, we see that that length right there is proportional, L, is proportional to the VSWR, to the reflection coefficient, to the reflection losses, you know, that aren't being passed down but are being reflected back, power losses, and I'll talk about those more. But what is this now? You know, if I were to draw a circle around here, and let me just do that. I think I've got, yeah, I don't know what that is. Okay, let's just take a length here, right? So there's my distance. And I'm just going to pop a couple dots here so that I can make a circle all the way around here. I think everybody can see what I'm doing. I'm using it sort of as a compass, protractor, whatever you want to call it, so that I can draw a circle. I should, now that I'm looking back at it, I should have drawn it in red, because then I could make out the difference between the black and the blue dots I'm drawing on here, which is sort of ridiculous, isn't it? But anyway, I'm going to draw that constant VSWR circle in red. Not well. I mean, I'll tell you that right now, but. Should have put some through there, I guess. Oh, wait, I did. There we go. I don't think that was so bad. So this big red circle that I've got here now is my constant VSWR circle. You're probably saying, well, it's not a constant anything, right? It's not a constant R circle because the R is changing all the time. And it's not a constant reactant circle because these are changing all the time too, and that's right. But what it is that it's a constant VSWR circle, and that's a couple things that you want to know. All the way at any point around that circle, I'm going to have a constant VSWR. So what does that tell me? At any point around that circle. So in the constant VSWR circle, let's just write this down. at any point along that constant VSWR circle that I've got here, all different impedances, everything else, I'm going to have the same reflection coefficient. I am going to have the same power coefficient. Oh, and what is the power reflection coefficient? That is just the magnitude of the reflection coefficient squared. All right. And I also want to point another thing out. You know, a lot of times in books you'll see rho as the magnitude of the reflection coefficient. So, you know, I'm not sure if your book used that or not. I can't remember. I always like to use the reflection coefficient because rho stands for so many other things. I don't really like to use it for that. This also tells us, because we know the VSWR, right? We can measure that and we know what the VSWR is going to be. And I'll show you that when we do an example on the actual Smith chart in the next lecture. So we know what all of those, for the constant VSWR circle, they're all going to have the same reflection coefficient. They're all going to have the same power reflection coefficient. They're all going to have the same VSR. That's why it's called the constant VSWR circle. And the last thing that they're going to have is they're going to have the same return loss, right? Because it's got the same reflection coefficient, they're going to have the same return loss there too. And I want to sort of define a couple of those. Now, the return loss in decibels, usually it's called RL, but the return loss in decibels is 20 times the log of the reflection coefficient, right? And you know, the reflection coefficient is also VSWR plus 1 over VSWR minus 1, right? So it's also then 10 times the log, because this is a velocity, this is a voltage ratio. It's 10 times the log of the power. 10 times the log of the power reflection coefficient too, right? Because since we're talking voltage, it's 20, and then we're basically squaring this, and so that's why we're using the relationship that the log of x squared equals 2 times the log of x. You see how all that works? And of course, we've talked about all those things before, and I'm sure that you've gotten all of those in network theory too, and everything. Now, let's extend this line. This is another thing that I want to teach you. I have no idea how long I've taken, but we're getting there. Now, if we were to extend this line, right, through the VSWR circle all the way to the other side, so right here, what we would see is we now have the reciprocal of the impedance of the load. Let's just look and see if that's true. Now we know that the impedance of the load, we said, was going to be 0.5, right? So there's my load impedance is going to be 0.5 minus j 0.5. Now, what would be the reciprocal of that? It'd be 1 divided by 0.5 minus j 0.5, wouldn't it? So what we'd want to do, right, so we're taking the reciprocal of this. So we've got 1 divide, well, yeah, I'll just do it this way. 1 divided by 0.5 plus j 0.5, 1 plus j 0, however you want to do it. And then we're just going to multiply it by I made a plus again. It's a minus. And then I want to multiply it by, let me get my other pen out. That's much better. Then I want to multiply it by its complex conjugate. So it's going to be 0.5 plus j 0.5, and then 0.5 plus j 0.5 up on top too. So if this is just really 1 multiplied by that, that's just 0.5 plus j 0.5. And then on the bottom, that's going to be 0.5 squared plus 0.5 squared. So that's 0.25 times 0.25, which gives me 0.5. And 0.5 over 0.5 is going to be 1. And 0.5 over 0.5 is going to be 1. So this gives me 1 plus j1, doesn't it? And now let's see if that's what we get over here. We can see that as I brought this around, well, that's not really a J1. I'm not sure exactly. That's like 1.4. So I obviously didn't draw this to scale. And then this one out here, what is that, 1.4? And that should have been a 1 too, right? So if this is 0.5, then I should have been 1 and 1. Wait, is that right? Did I do that right? 0.5 minus 0.5. And then I've got, yeah, it should just be 0.25 plus 0.25. That's 0.5. And 0.5, 0.5. So I actually, I obviously didn't draw this too well because it should have come out, that still doesn't seem right. It would have come out way over there. Did I draw it that poorly? if I drawn all of these things that poorly, I guess I have. Anyway, so it didn't come out exactly like I expected it to, but the other side is the admittance. So if this side is the impedance for the load, the other side is going to be the admittance for the load, right? And then we break it down into its conductance and susceptance. So we've learned a lot about the Smith chart right here. And what I want to do next is, a couple of things I'd like to point out. If we look at the VSWR on either end, either here or here, right, we see that the VSWR is going to be infinity, right? Because if I look at the VSWR, it's 1 plus the reflection coefficient and 1 minus the reflection coefficient, right? Or if I wanted to look at the equation for VSWR in my load, this would be 0. So this would be a short circuit, and this would be an open circuit. So if I've got a short circuit, we know the reflection coefficient for that short circuit is going to be -1. And so figuring out what the VSWR is, wait, I've got it, yes, it's 1 plus the magnitude, so 1 plus 1 over 1 minus 1, which would be infinity. So my line, my thing out here is a constant VSW, but that's the infinity. So VSWR equals infinity circle out here, all the way around. We'll talk more when we get to the next part about what it is that we do to actually match. How could we use a parallel stub match? And parallel, if you think about it, if we're putting things in, the circles, the red circle really is more for series components, and these are more for shunt components. And so we're going to see how we can put up a shunt line so that we can use a shunt line to match an antenna to the source, right? We're also going to look at if I was to put a line on here, what if I was to put a 1 meter or 2 meter line on here, right? For a, I don't know, 10 megahertz signal. How would that change the impedance? How would that, 2 meters of line, or what I say, 2 meters? I don't know. How would that 2 meters of line change the impedance that you would see from the source, right? Because now you've got the antenna out there and you've got 2 meters of line on that antenna, and that's going to change the overall impedance of the line plus antenna system, right? So you're going to have to come up with something to put in there as a shunt parallel stub match that will then bring it back to a matched load, and you'll be putting out as much power on that antenna as you possibly can, because that's what you want. You don't want any power loss reflected back. You want all the power going out. That's why you have to have impedance matching. All right, there's so much more I could talk about with the Smith chart, and I'll try to do it with the example that I do in the next lecture. And that's going to be the stub matching lecture, and that's going to be the end of the regular lectures. And then I'm going to talk a little bit about, I'm going to do a couple lectures maybe on Maxwell's equations and bringing all those together, because I think everybody really has already over the course of the semester used Maxwell's equations to do and seen how they all come together in a lot of ways, except for maybe the last one where Maxwell, added on to Ampere's equation. And I want to talk about how that really changed everything, and of course then changed his view of light had to be an electromagnetic phenomenon. And for a couple of days, he was the only person in the world that understood that salient point, that point, that changes everything, an understanding of light. Okay, talked probably too much, so see you in the next lecture tomorrow morning.